The tactical error took seconds, but physics made the outcome final. On July 19, 1545, the warship Mary Rose began a turn in the waters of the Solent. She was in action against the French fleet, and contemporary accounts suggest the ship carried a large complement of men and fighting gear for the engagement. Rebuilt around 1536, she likely came back heavier, toward 700 tons by some estimates, and with less stability in reserve. In the most widely cited reconstruction, a sudden gust caught her sails as she turned at close quarters. Under normal sailing, a ship of her class could heel, find her buoyancy, and come upright again. That afternoon, the reserve was already gone. The lower gun ports were open. To bring her heaviest cannons to bear on the French galleys, the crew had opened the square ports cut into the hull dangerously close to the waterline. When the ship heeled, the water did not wash against the timber siding. It poured directly into the gun deck. The influx of tons of seawater shifted the ship's weight instantly and catastrophically. The vessel lost all righting arm. She did not capsize slowly. She simply ceased to be a floating object and became a sinking weight. The speed of the event left no time for evacuation. The anti-boarding netting stretched across the upper deck, designed to keep enemy soldiers out, now kept the English crew in. Within minutes, Henry VIII's favorite warship, serving as Vice Admiral George Courou's ship that day, vanished beneath the surface. Contemporary accounts put roughly 500 men on board, with only a few dozen survivors. Later estimates vary. She settled on the seabed at a depth of roughly 40 feet. In the immediate aftermath, the water was shallow enough that the tops of her masts could remain visible, marking the gravesite. Early salvage attempts in the weeks following the disaster were frantic but primitive. They rigged cables to the standing structure and tried to heave the wreck free, but the strain broke the masts and left the hull embedded in the sediment. Then the silence set in. Over the next few centuries, the physics of the Solent worked on the wreck with ruthless efficiency. The local currents swept sand and silt over the site, but the process was uneven. The ship had come to rest on her starboard side at an angle of about 60 degrees, a position recorded during modern survey and excavation. The starboard half of the hull was quickly driven deep into the soft clay of the seabed. This immersion in the dense anaerobic mud sealed the timber away from the oxygenated water column. The clay acted as a time capsule, freezing the starboard structure in the 16th century. The exposed side faced a different fate. In the oxygenated water column, the ocean's biology went to work. Wood-boring organisms and erosion attacked the exposed timbers. Year by year, the portside structure weakened, collapsed, and was swept away by the tide. The decks disintegrated. The iron guns corroded into concretions. The upperworks dissolved into the drift. What remained was a specific and unusual geometric shape. It was no longer a ship in the traditional sense. It was a longitudinal cross-section, effectively half a hull, preserved almost perfectly on the right side and sheared off completely on the left. The surviving structure was a heavy oak shell containing thousands of objects, from heavy cannons to personal combs, all packed in dense clay. The environment that destroyed the port side had saved the starboard side by burying it. By the time the masts rotted away and the location was lost to memory, the Mary Rose had transformed from a shipwreck into a geological feature. She lay under a blanket of hard sediment, invisible to the eye, and undetectable by the technology of the era. The Solent currents smoothed the seabed over her grave, hiding the anomaly. For centuries, the site slid toward obscurity, its position blurred by shifting channels, imperfect charts, and the simple erosion of memory. There was no clear debris field to track. There was only a patch of gray mud covering a 700-ton oak structure that was slowly achieving chemical equilibrium with the clay. The ship was gone, but the physics trap that held her was just beginning to harden. The mud had preserved her, and it would not easily let her go. 437 years is a duration that usually erases all trace of organic engineering. In the high-energy environment of the English Channel, wood is food and currents are abrasive. By all conventional logic, the Mary Rose should have been nothing more than a scatter of bronze guns on the seabed. But sonar began to hint at a coherent anomaly in the late 1960s, and in 1971, the evidence on the trace and divers' confirmation showed that something large still lay buried beneath the sediment. Historian and diver Alexander Muki had spent years searching the Solent for the lost flagship, fighting the assumption that she had been destroyed. The hull survived through chemical isolation. When the ship hit the seabed in 1545, the starboard side drove deep into soft clay and was sealed off from oxygen. In that low oxygen pocket, the usual rot could not complete its work. The timber was preserved, but it was fundamentally altered. Over 4 centuries, the water had leached out the cellular structure of the oak and replaced it. The wood was now waterlogged and soft, possessing a consistency often compared to wet cardboard. It retained its shape only because it was supported by the surrounding mud. Exposing this fragility required a surgical approach to excavation. The divers could not use shovels or mechanical dredgers which would slice through the softened timber like butter. Instead, they utilized a tool known as the airlift. A long pipe was held vertically in the water column, and compressed air was injected near its base. The rising air reduced the density inside the pipe and drove a fast upward flow, carrying water and loosened sediment up and away from the site. In practice, it worked like an underwater conveyor for silt, capable of moving tons of overburden without touching the delicate surface beneath. The operation was conducted in conditions that bordered on impossible. The Solent is a busy shipping lane with fast, turbid tides. Divers often worked in total darkness, unable to see their own gauges. They guided the roaring suction intake by hand, feeling the texture of the seabed. They had to distinguish between the hard clay, the soft artifacts, and the degraded hull timbers by touch alone. It was a slow, blind process of disinterment that required thousands of dive hours to clear the site. As they stripped away the protective blanket of mud, the true scale of the remnant was revealed. The starboard hull stood several deck levels high, with partitions, cabins, and companionways intact. It was a cross-section of Tudor life, frozen in time. However, the act of excavation introduced a new and immediate threat. The mud that had hidden the ship was also the only thing holding it together. As the divers removed the clay, they removed the external support for the weakened timbers. The hull was no longer a rigid structure capable of withstanding stress. It was a heavy, water-saturated sponge that would collapse under its own weight if handled incorrectly. The team found themselves uncovering a massive object that was chemically stable while submerged but mechanically incompetent. They had proven the ship existed, but in doing so, they had started a clock. The protection of the anaerobic seal was broken, and the physics of the open ocean began to reclaim the site. The challenge shifted from finding the wreck to preventing the survey itself from destroying it. The geometry of the Mary Rose presented a salvage problem that had no precedent in maritime history. Most shipwrecks sit on the seabed as a chaotic pile of debris or a relatively intact structural box. This wreck was a clean, brutal asymmetry, one surviving shell, still packed with heavy clay. This created a profound structural imbalance. There were no deck beams spanning the width of the hull to provide rigidity. The surviving shell was an open shape, like a canoe cut in half down its center line. If any force were applied to the sides, the lack of internal cross-bracing meant the hull would simply fold inward and crumble. This geometric fragility ruled out every standard method of recovery. In a conventional salvage operation, engineers would pass heavy steel cables or straps underneath the hull. These straps would form a cradle, and cranes would hoist the vessel to the surface. But for the Mary Rose, the compressive force of lifting straps would act like a giant fist closing around the timber. The waterlogged oak, with its degraded cellular structure, possessed zero resistance to crushing. A strap lift would not recover a ship. It would recover a pile of splintered lumber. The engineers were facing a heavy lift scenario where they could not touch the object they intended to move. The challenge was compounded by the nature of the seabed itself. The hull was not merely resting on the floor of the Solent, it was embedded deep within the sediment. Over 4 centuries, the clay had settled around the timber, creating a powerful adhesive bond. Salvors call it suction, a mud seal that can resist lift with forces far beyond dead weight. If a crane simply pulled upwards, the clay would hold the ship down. The tension would build until the weakest link in the chain failed. In this case, the weakest link was the ship itself. The keel would likely remain stuck in the mud while the upper works were torn free, destroying the vessel in the process. The engineering team had to solve a paradox. They needed to apply a massive upward force to break the suction, but they could not apply any pressure to the fragile hull structure. They had to find a way to distribute the lifting load so evenly that the soft wood would not sense the strain. The solution required a complete inversion of salvage logic. Instead of wrapping the ship from the outside, they would have to find a way to engage the structure from within. They needed to turn the hull into its own lifting frame, using the strength of the original 16th century skeleton to defeat the grip of the clay. The mud had saved the ship for 400 years, but now it was the enemy. Brute force would mean total loss. The only path forward was to pull her free by spreading the load through the structure itself, an approach that demanded controlled intrusion. The decision to drill holes in a unique archaeological artifact is one of the most difficult trade-offs in conservation engineering. The salvage team faced a brutal binary choice. They could wrap the hull in straps, which would almost certainly crush the waterlogged timber, or they could mechanically invade the structure to install an internal support system. They chose the invasion. The logic was that a series of small, controlled punctures was preferable to a catastrophic structural collapse. This decision initiated the fabrication of custom through-bolt and backing plate assemblies, the hardware that would define the entire operation. The toggle bolt was not an off-the-shelf component. It was a purpose-built interface designed to transfer the weight of the ship to an overhead gantry without compressing the wood. The concept was simple but invasive. A diver would drill a hole through the original hull planking. A long iron bolt was inserted from the outside. On the interior of the ship, a large steel backing plate was secured to the bolt. When the bolt was pulled from the outside, the backing plate would press against the inner surface of the hull. This spread the lifting force across a wide surface area of timber, utilizing what compressive strength remained while avoiding the crushing grip of external straps. To support this suspension system, a massive exoskeleton was required. The engineers deployed the underwater lifting frame, a four-legged table of tubular yellow steel often referred to by the team as the spider. This structure was lowered until it straddled the wreck site, its feet planting into the seabed outside the perimeter of the hull. It provided a rigid, level datum line above the chaotic geometry of the wreck. The frame was the anchor point for the entire lift, designed to bear the full load of the ship once it was free of the bottom. The installation phase demanded extreme human endurance. Divers worked in the fast-flowing, murky waters of the Solent to prepare the hull. They had to drill roughly 170 individual holes through the oak timbers. This was precision carpentry performed in conditions of near-zero visibility. The divers often worked by touch alone, guiding the drill bits with their hands to avoid hitting hidden iron fasteners or structural knees. Every hole had to be perfectly aligned to accept the bolt and the backing plate. A mistake here would not just damage the wood, it would compromise the lifting geometry. Once the bolts were seated, the wiring process began. The team connected the external eyelets of the bolts to the steel frame above using high-tensile wires. They rigged 67 primary lifting points along the length of the keel and the ribs. Turnbuckles allowed the engineers to adjust each line, and simple telltales helped them monitor how the load was sharing across the hull. The engineers had to balance the load across the entire length of the ship, ensuring that no single section of the hull carried more weight than it could bear. It was a process of tuning a massive instrument. As the wires were tightened, the ship was effectively transformed. It was no longer a passive shipwreck resting in the mud. It had become a suspended object, a marionette strung to the steel spider above it. The integration of the toggle bolts and the lifting frame solved the problem of handling the fragile wood. The hull was now mechanically locked to the modern steel structure. However, this assembly was still pinned to the bottom by the suction of the clay. The engineers had built the machine that would lift the Mary Rose, but they had not yet tested it against the grip of the seabed. The static rigging was complete. The components were joined. The operation now faced its most critical transition, the application of vertical force against the resistance of the earth. The maneuver known as the underwater transfer is a high-stakes geometrical puzzle played out in a blind environment. By October 1982, the Mary Rose was no longer a passive element of the seabed. She was hanging suspended from the yellow lifting frame, held in place by the 67 wires connected to the toggle bolts. But the ship could not simply be pulled to the surface. The waterlogged timber was too fragile to support its own weight in the air. If the crane lifted her out of the water while she was hanging from the wires, the hull would likely tear itself apart under the force of gravity. The engineers had to place the ship into a supporting structure before she broke the surface. This requirement dictated a complex two-stage operation. First, a massive steel cradle, cushioned with inflated airbags, was lowered to the seabed near the wreck. This cradle was the shipping crate that would support the hull during the final ascent. The plan was to lift the frame and the ship together, move them laterally through the water, and lower them gently into the waiting cradle. Only when the frame and the cradle were locked together, a process called mating, could the entire assembly be raised to the air. The heavy lift vessel Togmore arrived on station to execute the pull. She was equipped with a 1,000-ton class heavy lift crane, a margin of safety that seemed sufficient for the calculated load. The first step was to break the suction of the clay. The engineers activated hydraulic jacks located on the forward legs of the lifting frame. Slowly, they pushed against the seabed footings, forcing the frame upward. The hydraulic pressure fought the grip of the mud inch by inch until the seal cracked. The Mary Rose was free of the earth for the first time in 437 years. The transfer phase began on October 10th. The crane lifted the frame and the hanging ship and began the lateral move toward the cradle. It was a delicate operation involving hundreds of tons of steel and wood moving in a current. As the frame was lowered toward the cradle, a guide leg designed to align the two structures bent under the load, and the team had to cut away the damaged steel. Later, during a change in the lifting slings to take on the added load of the cradle, one strop was fitted incorrectly. The weight redistributed in an instant. A sharp metallic crash rang out as the package lurched and a corner of the steelwork slipped. For a few seconds, it appeared the lifting frame might come down onto the hull. But the rigging held, the frame steadied, and the project escaped with damage that was frighteningly loud and mercifully limited. With the crisis stabilized, the team completed the mating sequence. The legs of the lifting frame stabbed into the guides of the cradle. The two steel structures were locked together, sandwiching the Mary Rose safely between them. The load was now secure. On the morning of October 11th, the Togmore throttled up its winches. The wire ropes tautened, and the hundreds of tons assembly began the long ascent to the surface. The operation had defeated the mud and the gravity of the ocean floor. But as the yellow frame broke the waterline, the salvage team faced the final boundary. The ship was leaving the chemical safety of the salt water and entering the hostile chemistry of the atmosphere. 19,000 is a number that reshaped the understanding of Tudor maritime history. When the Mary Rose cleared the water of the Solent, she brought with her a collection of artifacts that exceeded the inventory of many national museums. The recovery yield included heavy bronze cannons, complete chests of carpentry tools, medical supplies, longbows, and the personal effects of the crew. However, the sheer volume of these objects presented an immediate logistical crisis. Every single item, from the massive oak hull to the smallest leather shoe, had been stabilized by the anaerobic conditions of the seabed. Once they met air, the seabed's anaerobic shield no longer applied. The salvage team had beaten gravity, but now they were racing oxidation and dehydration. The timber was still as soft as the engineers had warned from the start. While submerged, the water filled the degraded cells and maintained the shape of the wood. If the water was allowed to evaporate, the cell walls would collapse. The timber would shrink, crack, and eventually disintegrate into dust. The ship had survived 4 centuries of immersion, but it would not survive a week of dehydration. To prevent this destruction, the engineering team had to construct a life support system for a dead ship. The Mary Rose was placed in a dry dock that was immediately converted into a controlled chamber. A complex grid of pipes and nozzles was installed around and inside the hull. For years after the lift, she was kept continuously sprayed with fresh, chilled water to slow biological growth and begin stabilization. In the mid-1990s, beginning in 1994, conservators introduced PEG, polyethylene glycol, a water-soluble wax that gradually replaced water within the timber. That long treatment ran for decades, and by 2013, the hull moved into controlled air drying, with humidity managed so the wood would not collapse as it finally let go of the sea. The success of the operation was defined not just by the raising of the hull, but by the integrity of this forensic evidence. The Mary Rose was a sealed Tudor snapshot, closed in 1545 and opened in 1982. Because the silt had covered it so rapidly, the site offered a snapshot of a working warship in its final moments. The position of the men, the state of the weapons, and the contents of the galleys were frozen in the mud. The recovery confirmed the value of the forensic approach. By treating the wreck as a crime scene rather than a treasure trove, the salvage team had preserved the context of the disaster. They had solved the engineering paradox of the lift, using the toggle bolts and the frame to support the fragile hull. And they had executed the transfer without destroying the artifact. The decision to cut the suction with hydraulic jacks, the risk of the underwater mating, and the terrifying slip of the lifting frame all culminated in this result. The ship now sits in a controlled environment, no longer a wreck at the bottom of the channel, but a standing structure. The operation proved that it was possible to recover a large-scale, waterlogged biological structure from a high-energy marine environment. It required the invention of new hardware and the application of industrial lifting capacities to a delicate archaeological problem. In the most widely cited reconstruction, one hard heel with open lower ports finished her. She returned as a massive data set, proving that with enough engineering precision, even the damage wrought by 437 years of immersion can be reversed. The physics of the loss were absolute, but the physics of the recovery were, in the end, superior.